Thank you for the introduction and thank you for the invitation to the organizer. So I will try to find some ghost of integrability, even if the system, the dynamics is not integrable and even chaotic. And maybe I begin to say what I will call integrability. So M will be a closed manifold. And we will be on the cotangent bundle. And on the cotangent bundle, there is a more or less canonical symplectic form that you can write in coordinates Q and dual coordinate P. Okay, and if n is the dimension of M, something like that. Okay, and what is integrable for me is very simple. This means that you have a flow. So it's a flow even if the main part of our results are valid on in the non-autonomous case for symplectic diffeomorphism. So, or conformally symplectic, I will explain what it is. So it's a flow that preserves Lagrangian submanifolds. So this means that the pullback of the symplectic form is a constant. Well, that is positive. And when A is equal to 1, the flow is symplectic. So I will look at this kind of flow that can be Hamiltonian, but also what is called conformally Hamilton symplectic. When you change the symplectic form up to a constant, multiplicative constant. Yes, so you can ask why I wrote T and here a constant. In fact, you can prove that if the dimension of M is at least 2, A has to be a constant. It cannot change. Okay. And so integrable means that M is as a partition into Lagrangian sections that are invariant, flow invariant. So for example, the pendulum is not integrable for me because there is some height at the middle. So this is my definition of integrability. So you have the partition into Lagrangian graph. And in some cases, there are existence of some generalized Lagrangian manifolds that are invariant, and I will explain which. It is in the setting of Wickham theory. So you assume that you have a Hamiltonian that is convex and superlinear. Sorry, I'll put some noise. This one? I have to move this. Okay. Okay. And superlinear in the fiber direction. Then in this setting, you say that H is tonally. Fatty proves that, and there are also work of Maslov, Manier, and other people. But Fatty proves that there is a kind of forward or backward, I will say backward, weak invariant, well, backward invariant It's not really a foliation because it's not really a partition, and the union of the invariant submanifold is not the whole space. But you have so union of weak Lagrangian submanifold. So these are discontinuous submanifold that is in T star M. And so you have this kind of weak foliation. For example, in the case of the pendulum, this foliation is, well, maybe it's not so interesting. I will draw something else. So I draw something that you could imagine that is, so it's backward invariant. It can be two graphs, but it can be also disconnected graphs that are backward invariant. For example, here I have a fixed point with it part of it unstable manifold. And so it's backward invariant, and you have a kind of partition, yes, no, subset of the cotangent bundle. And in this invariant submanifold, there are invariant measures always. So these are only backward invariant, but you can have support of invariant measure. And so this is the work of Maslov. So always in the tonally case, you have invariant measure that are minimized. I define this, but they minimize some Lagrangian action. And what is interesting is that this implies that there is no conjugate point. So what is a conjugate point? Along the orbits in the support of the minimizing measure. This means that if you take a point on T star M and you look at what I call the vertical. So what is the vertical? It is the tangent to the fiber. So if you take the image of the vertical along an orbit, so this is d phi t of b of x. So you arrive at a point that is phi t of x. This is transverse to the vertical at the considered point. So if I take the image of this vertical by the flow, I have something that is transverse. And so in the future, for example, the forward image of the vertical, they don't meet the vertical at the considered point, except in 0. Okay. So the image of the vertical, they don't oscillate, they don't meet the vertical, so they are in some part of the Lagrangian manifold that I will define now. What is the meaning of tonally? Yeah. Superlinear, it grows more than any linear function. So the limit when p goes to infinity of h of qp, it's uniform in q, is plus infinite. Okay. And for example, you have, if you add, of course, geodesic flow, it's okay. And also you can add a potential. So you have mechanical systems that are example of such dynamics. Superlinearity? Yes, yes, true. Yes. Yes, it's like twist. If you are more familiar with the twist condition for twist map, it's exactly twist. So the twist of the vertical. Okay. Okay, but there are very simple examples where all the points are conjugate points. Maybe we can say, okay, the generalization of integrability is to look after point with where you have no point where you have no conjugate point, but in fact, it's very easy. If you conjugate an integrable system, you can have, for example, in dimension 2, this kind of things, it's very easy to, and along every orbit, of course, you have conjugate points, and it's not very, in fact, you think that it's integrable, even if you have conjugate points. So this kind of property of integrability, if you want some part of integrability in a non-convex setting, is not a good idea. And that's why we look after points with 0 Maslov index. And so I have to define what it is. So I will introduce some notations. So L is the set, is a Grassmannian of Lagrangian subspaces of T, the tangent space of T star L. So at each point is a symplectic space, and I take the Grassmannian. Then V is a manifold, the submanifold. It's just the set of the vertical subspace. So these are Lagrangian subspace. Okay. Sigma 1 is the set of the Lagrangian subspace such that the dimension of L with V at the considered point is equal to 1. Okay. And sigma that is called sometimes the singular locus is the set where dimension of Lagrangian space where the dimension is larger than 1. Okay. So sigma is the complement of the set. Wait. Where is 0? What do you say? I think it's all. Okay. And now I consider an arc of Lagrangian subspace, and I assume that at A and B, gamma of A and gamma of B are, so they are not in sigma. So I want to define the Maslov index. And so I have this property that if in the homotopy class, excuse me, with fixed n of gamma, then the set of arcs that don't meet, so sigma minus sigma 1 and arc transverse to sigma 1 is open and dense. So there are general arcs in the homotopy class of gamma, for which there will be easy to compute the number of intersections with V. So arcs gamma tilde, set of arc gamma tilde. So I won't give it precisely, but I put some co-orientation on sigma 1. The algebraic number of intersection of gamma tilde with sigma 1 is something that depends only on the homotopy class, that is constant. And so this is the Maslov index of gamma. And the Maslov index is 0 when, so either you don't meet the vertical along the arc gamma, or you meet the same number in the positive sense or in the negative sense. I'm not very interested in the orientation because I'm just interested in 0 Maslov index. Okay. On a Lagrangian graph, so if you are on a Lagrangian graph and you follow the tangents n, if gamma takes its values in the tangent space of n, then in fact there is no conjugate point along gamma and the Maslov index is 0. Okay. you don't meet the vertical. And when gamma is defined on the half line, and when it exists, the asymptotic Maslov index is the limit when t goes to infinity of 1 over t me of gamma restricted to 0t. So it's a kind of mean value of the number of times you cross the vertical, your arc of Lagrangian subspace cross the vertical. Are there some questions? So for example, along this curve, the Maslov index, the total, yes, excuse me. N, on a Lagrangian graph N, if gamma is take its value in the tangent space, in fact, there is no conjugate point along this arc. And so the Maslov index is 0. You never cross the vertical because it's a graph. Every arc, yes.
When you say the project graph, you mean just the graph of the proton?
It's a section, yes. It's a graph of a C1 map, yes. Yes, because if it's a graph with a vertical tangent space, yes. It's a closed one form. Yes, yes. Okay, I just need to define what is a dynamical Maslov index. So I consider only arc that has the image of some Lagrangian subspace. And when it exists, so I consider the infinite Maslov index of gamma. And it can be proved, so I will assume that L is in the tangent space at some point x. It can be proved that it's independent on L. It depends only on x. And so it's a dynamic Maslov index of x. Okay, and there is a result of Ruel. That says that if you have an invariant, if mu is an invariant probability measure with compact support, then almost everywhere the dynamical Maslov index is defined. And moreover, if you define so this quantity, so it's integrable in fact, If the measure is ergodic, almost everywhere you have that the Maslov index is the Maslov index of the measure. But if mu is not ergodic, in fact, sometimes there doesn't exist x in support of mu, such that in particular, if you find an invariant measure with 0 Maslov index, it doesn't mean that you have a with 0 Maslov index. Are there some questions? No. Okay, so now I will give the first statement. That we prove so we assume that we have a conformal Hamiltonian flow, like at the beginning. And then that n is a Lagrangian submanifold. And we need some topological assumption of this Lagrangian submanifold that is homotopic to a graph among the Lagrangian submanifold. And such that its positive orbit is relatively compact. So for example, if you have an Hamiltonian that is proper, this condition is not a condition because the energy is preserved. And so if you have your manifold, she will stay in some compact. She will remain in some compact. Then there exists a Borel probability invariant such that so the Maslov index is 0 with support in this set, no, more than this set, in the intersection okay. As I said to you, this doesn't imply the existence of this one point with 0 dynamical Maslov index, because maybe this measure is not ergodic. what we prove is that you take any manifold with Lagrangian manifold, not necessarily a graph, but the topic to a graph, you will find in some compact part an invariant measure. So something with vanishing Maslov index. If we want to find points, we need another hypothesis that is similar to twist, but a little less, because in twist there is a strict convexity, and we realize that we only need a kind of convexity. So now we will add a twist hypothesis. Okay, I won't give the definition in detail, but okay. I will take some particular Darboux charts that I will call vertically and what it means is that, okay, you have a product. So if the dimension of the manifold M is n, this is the image of my chart, and these vertical leaves correspond to the vertical leaves in the cotangent bundle. So this is the vertical foliation in the chart. And so for this, I won't write everything, but locally, we ask that. And for small t, so the image of, this is F, of each vertical leaf is, so I will draw this, something, I don't know exactly what it is. It's a graph, but from this set to this set. So it's a graph, and because it's Lagrangian, it's a graph of some DGT. And we will ask something that is a twist condition. So for T small positive, GT is convex, but not strictly convex. And for T negative, GT is concave. And this is an extension of the twist condition. If you ask this condition, you can modify the theorem. So, condition. So you assume that phi t is a conformal symplectic flow plus the twist hypothesis. You ask the same, no, you ask that n is Lagrangian plus homotopic to a graph among the Lagrangian submanifold. Okay, and what you can prove is that there exists at least a point in N with 0 Maslov index. And if you add the hypothesis about the compacity of the orbit of the manifold, so if is compact, then you find an ergodic measure. Is mu ergodic with support in the same set than before with 0 Maslov index. And in general, you find a lot of different such measures, because if you change your manifold, you change the cohomology class, because so you can associate to each such manifold a cohomology class on M. If your cohomology class is very large, you can find a lot of different invariant measures. And there is a corollary. That is that the set of points with 0 Maslov index for some manifolds, you can give a lower bound of this. For example, for the tori, if M is Tn, then the Hausdorff dimension of the set of X with, so the same hypothesis is with 0 vanishing Maslov index is bigger than N. And if you look at the example of the damped pendulum, you can prove that it's exactly N in some cases, yes. Oh, I have no idea of that. I don't know. In fact, what we find is a measure that is not ergodic, but we can prove that all the measures in the ergodic decomposition have 0 vanishing Maslov index, but we don't know if they are uniquely ergodic. No idea. Okay, and also I can mention that in Tonelli flow, and when N is a section truth, what we find are the minimizing measure of Maser. But when N is not a graph, it's not so obvious, we don't know. And the idea of the proof, very quickly. So there is a statement in finite time that is that, so you take N, or N like this. Or even I will take a graph, it's more. Okay, N is a Lagrangian graph. Okay. You imagine you have a graph and you take in finite time by 1, for example, the image. So by any conformal symplectic flow. So maybe it's not a graph, but it's Lagrangian. And what you do is for people that do symplectic geometry, you use a selector, what is called a selector of graph, that give you a discontinuous Lagrangian graph via symplectic geometry. Selector of graph. And what you can prove is that all the points here if you look at the image of the tangent space to this Lagrangian graph along the flow, maybe sometimes it turns. It can happen, maybe I will draw some suggestive. But at the end, when we arrive, the Maslov index is 0 in finite time. And so to do that, there are 2 steps. The first one is to prove that if you take a curve on this manifold with 2 endpoints on the graph selector, then the Maslov index is 0. And then you have to prove that to go from this point to this point, this implies that the Maslov index of all the points is constant. And to find the constant, you use the continuity of some integer from T. Okay, and to find the measure, you have to take the limit in infinite time. It's more or less standard, to be careful. And so for the end, in this case, when you obtain a measure that is invariant with 0 Maslov index, in fact, you can prove that. So when I define the Maslov index of a measure, I said is the integral of some function, you can prove that this function is, for example, non-negative. And so because the integral is 0, it's 0 everywhere. Okay, and so this will give you the conclusion. Okay, thank you for your attention.
Please give an example, some kind of figure. I don't feel with conformal symplectic stuff. Do you have in mind some example which?
Yes, of course. First, an example of conformally symplectic dynamics. It's just a dump. So you take any Hamiltonian dynamic. So, well, I will be in coordinates, something like that, plus what is called the Liouville vector field. And the Liouville vector field, it's just the vector fields that correspond to the homothécy flows in the fiber direction. And so, for example, in there is a very nice article of Maro and Alfonso Sorrentino on discounted, what is the title? Conformally symplectic, conformally Hamiltonian Tonelli dynamics, I think, where there is a picture on what happened for the pendulum, the down pendulum. Okay, you have an elliptic point that becomes attractive, and then so almost all the orbits turn to this elliptic point with rotation. So the asymptotic Maslov index is not 0, and the only points where you have zero asymptotic Maslov index are on the unstable manifold of the hyperbolic singularity. So it can be very small.
Like your Maslov index always on all this point, right?
This in this case, yes. Not for this statement, but for this statement, yes. Yes, yes. You always increase index, yes. Yes, yes. You can give a statement that are more symplectically invariant by saying that there is a foliation Lagrangian that you meet always the same sense. Yes.
Thank you very much.
Thank you.